Alrighty, gang, I apologize, but I missed the first part of the lecture. The recording's gone. So, what have we done? We've created a new project. Call it Lecture B. And then once I created a new project, I added a new CPP file by going to Source Files, right-click, Add New Item, and called it lectureb.cpp. And then just pause your recording and type this in. Right. So that's working. Now let me come back and answer your question. I'm sorry. So I'm going to take my source code as I've typed it so far, and I'm going to save it as boilerplate. You know what? There's an easier way to do it, probably. We could just probably do file save as, but then we'd have to close and reopen it once we did that. So I'm going to do it differently. So I'm going to launch Notepad. I'm going to paste it, and I'm going to do file save as, and I'm going to save it to my desktop, or whatever folder I want, as boilerplate. From here on out, I'm probably just going to open that file and copy and paste whenever I create a new file. Boilerplate.txt. Okay. So what's the first thing we're going to do every time we work on one of these programs? We're just going to delete the hello line and start putting our code there. Now we don't hardly know why we have this statement here, right? We don't understand yet what a lot of this syntax means, but we will pick it up and we will talk about those things. All right, we had an algorithm we were going to follow. Here's our algorithm. Ask the user for their height. I mean, we could even label them, right? Steps A, B, C, D, E, and F. Ask the user for their height. So we're going to need some output and input statements. Output is done with cout, arrow, arrow, with the arrows going towards cout. And when I say arrow, arrow, I mean less than, less than. And input is done using cin, arrow, arrow, but the arrows are going the other way. And we're going to need some variables to store this data in. Now that wasn't part of the algorithm. The algorithm doesn't care whether we have variables or not. It tells us their names, but it doesn't tell us that we have to declare them. But we know that in this language, in C++, variables must be defined before they can be used. That's different than Python. In Python, it was fine to do age is equal to 32 and just, rock and roll with that. In this language, we would have to give it a data type first. We'd have to say, oh, this variable can hold an integer, and oh, here's the integer that it's supposed to be holding. And once you create a variable, you can't change its type. You can't go, okay, age is equal to Fred. Now, why would you do that? I don't know. But, once you declare x as an int, you can't then turn around and try to store a floating point value in it or store a word in it, right? These will be syntax errors. They would not be in Python. Python doesn't care. Python will erase that variable and recreate it on the fly in order to hold the data that you're telling it to. Okay, so we're going to need what variables? This recipe, this algorithm mentions 3 variables. What are their names? Not a rhetorical question. I want somebody to tell me the names of the variables that they see in the algorithm. Right, so we have 3 of them. And we're going to make them floating point variables. Why? So that, if the user wanted to say that they weigh 195.2 pounds, they get to type in the 0.2. And since we're doing division. So we're going to need 3 variables. This algorithm requires 3 variables. And we're going to make them of type double. We don't even know what a double is. It's a floating point type. It's a very precise floating point type. We will make them type double, which is a double wide float. Double wide meaning it takes 8 bytes rather than 4 bytes to hold it. Okay, let's go do that. We need our 3 variables. Got to go to my source code and declare 3 variables. Double, I could declare them 1 per line, or I could declare them all at the same time. Let me show you what I mean. Height, I could do that, and then I could do double weight, and I could do, or I could just do this. Double height, comma, double HT, comma, WT, comma, BMI. There's nothing wrong with declaring your variables on the same line if they are of the same type. On the other hand, I would argue that it's not a bad idea to go ahead and do it one per line, like this. Double height, and that way I could add some comments. Height in inches. Double WT, semicolon. Weight in pounds. Have you ever wondered why LB means pound? And then double BMI, which is going to stand for body mass index. We haven't even started with the algorithm yet, right? This is just all the framework required to get to the point where we can start actually entering some code that implements that algorithm. Step 1, ask the user for their height. So we're going to need a cout statement. Cout, and when I say arrow, arrow, in this case, I mean less than, quote, what is your height? Or what is the height of the patient? Or something like that. What is your height, question mark. Space, space, end quote, semicolon. Now, I have decided that I like putting a little symbol that tells them where to type. So I am going to put that little greater than sign before the quote, just so that the user knows where to type. There'll be a flashing cursor anyways, but I've decided I like that. Now we need to give them a chance to type it in, just like the input function in Python. CIN greater than HT. In other words, take from console, whoops, not CINT, just CIN. CIN greater than HT semicolon. Cout stands for console output, display to the console this message. This stands for console input. Wait for the user to type in this input and store it into that variable name. All right, we've done the first part of the algorithm. We've done steps A and B. We're going to do the next thing, ask the user for their weight and store the result in a variable. So cout error error quote, what is your weight, question mark, space space greater than, semicolon. Now one thing to note is that cout does not go to the next line. If you've done Python programming, you're used to the print statement taking you to the next line. Well, cout doesn't do that. If we want it to go to the next line, we have to specifically say to do so. Not doing so yet, but we probably will when we display the results. CIN error error, what is our weight variable called? It's called WT. Cout greater than WT semicolon. All right, I've done so much typing that I want to run the program and make sure that it works as is. Just like voting in Chicago, vote early, vote often, I'm going to run early and run often. I like to keep my program in a working state at all times so that if there are any syntax errors, I figure that out before I've sat down and write 400 lines of code. Now, it's not going to do anything. It's not going to do its calculation, but it is going to ask me, what is your height? Right? My height is, I'm 6 feet tall. Yeah, right. 72 inches. My weight, I'm a linebacker. I weigh 300 pounds. Okay. And it says hello. I need to delete that line. I don't want it saying hello. But you see why I put the little cursors there? Maybe you don't like them. You can take them out if you don't want them there. All right, I need to delete that line. Anybody got a syntax error at this point? All right, I'll be right there. All right, when you're installing Visual Studio at home, it's possible that it's not going to let you make a C++ file when you do File New Project. If that's the case, run the installer again and select C++ as the option to install. and then it gives you a list of optional files. Just click everything that says C++, and that ought to take care of it. Okay, so let's calculate our BMI. BMI equals, and I think I remember the formula, 703 times our weight, WT, divided by slash, and we need to take our height squared, so parentheses HT times HT, end parentheses, semicolon. Now, if I didn't have any Mac users in the class, then what I might have been tempted to do, don't make this change, is do POW parentheses weight, comma 2, or height, comma 2. Take the height and raise it to the power 2. And that's great and all that, but well, not unfortunately, Microsoft is non-standard by giving you the POW function without using an include. We're going to add an include to support POW if we wanted to. We would come up here and we would add one more # include. As a matter of fact, at some point I'm going to add this to my boilerplate. But I would want to do include angle CMath, and then I would get that PW function. Include angle CMath, close angle. But even though I've done that, I'm going to go back and change this to the way it looked before. That makes it just look a little bit more arcane. So I'm going to do that. Divided by open parentheses HT times HT. If you want to use a POW function, like I showed you, you can do that. Inside those parentheses, do POW HT comma 2. Raise HT to the power of 2. And then we need to display the results. Cout less than, quote, BMI calculated as space, end quote, arrow, BMI. Now I'm going to make a mistake, and then we'll fix it, just to prove a point. So I'm going to run it. It churns along. What's my height? 72 inches. I'm 300 pounds. BMI calculated as 40.6829. Press any key to continue. All right, that's kind of lame, but it's illustrating that the print statement did not go to the next line. So we're going to add something to our print statement to go to the next line. We're going to add a new line. There's two ways to add new lines, and you'll see me use them both. One is that you can use the \n character. We could even put that on its own line if we wanted to. We could do this, cout, and I'm going to undo this, so don't necessarily do this. Cout error quote, \n, end quote, semicolon. That would go to the next line. That \n means new line. But there's also a specialized word meaning end of line, new line, that we can use with cout. And so I'm going to delete temporarily that semicolon there and do less than, ENDL. That's not END1, it's END lowercase l. That means end of line, it means new line. If you don't like seeing ENDL, you could replace the word ENDL with quote \n, end quote. Works just as well. Programmers who are not familiar with the C++ programming language and IOStream would probably rather see that, because all programmers after a certain point know what \n means. However, all the book examples are going to show using ENDL, so I'm going to leave that for now. Now we ought to be good. What's your height? And my height is 72 inches. What's your weight? I weigh 300 pounds. Your BMI is calculated as 40. Now, all BMI is body mass index. What it means is a ratio of height to weight. And it's kind of like those insurance tables, right? Ooh, it looks like you could lose some weight. Or, you're dangerously underweight, so you either become a fashion model or, start eating. I'm making jokes here. But You know, that's what BMI is used for, but it's not a real reliable measurement on a person-by-person basis. For example, a football player or bodybuilder or whatever will have a really high BMI, even though they may be very healthy, right? Just because, you know, they have a lot of muscle. And so don't take any information that we're getting from this as, you know, indicative of anything in particular. It's just a formula. That's it. That's a particular interest. I use it because it requires two pieces of data and a formula and an equation, right? And it's more interesting perhaps than just, you know, hours times pay rate, which you get tired of typing in. Okay, so we've written a program and it followed our algorithm. We're feeling pretty good about that. Anybody need any help getting this to run?
Do you care how we go to that next space? Like the end L, or do you? Like,
I have no, yeah, that's your preference. Whatever you like. You like using \n? I like \n. You'll see me vacillate between them. And what do I mean by that? If I do this, cout error, error quote, program done, you don't have to do this. I'm just making a point. I could do this. That works. Or and that's what the book will show. Or I can just do that. I'd rather do that. It's fewer keystrokes. So if I already have a string quote open and I want it to go to the next line, I'm just going to use \n. But that wasn't the case here, was it? Right? I didn't have a quote open. So I went ahead and used ENDL. Not that typing in quote \n end quote takes any more characters than ENDL. So you can just pick one way. I don't care if you toggle between the two or totally inconsistent or whatever. Your choice, though. Good question. All right. Any questions so far? Let's dig into what this is. These are keywords. All these blue things are keywords. All these white words, or at least a fair number of them, are what are known as identifiers. Identifiers are variable names. And this is a variable, even though it doesn't look like one because we didn't create it. Or function names. That's a function. And then we have constants. This is an unnamed constant, also known as a literal. It's literally typed into the code, right? Because if I find out that science has decided that 703 isn't the right ratio and it needs to be 708, if I don't have the source code, I'm stuck. I'm out of luck. I can't change it. It's hardwired into the program. It's hard-coded. That's a term I will use, meaning that there is a constant, an unnamed constant, literally hard-coded into the program. Some people also call them magic numbers. Like, what in the world is 703? Why did we pick that? Well, it might have been nice if we had declared a constant that had that number. Like const int, you know, conversion factor, right? Don't do this. I'm probably going to undo it because it's too much typing, you know, or English or imperial conversion factor equals 73. Now that's becoming a little bit ridiculous, right? That variable name is a little bit too long. But, you know, our constants may have been defined up here at the top, you know, or in some header file. When we're scrolling down here and we're looking at our code and we see BMI is equal to English conversion factor, at least we have a clue of what's going on, right? Or BMI conversion factor or something, some descriptive term. Now I'm going to undo all those changes and I'm going to leave it back as it was, a 703. This is what's known as an expression. It's an algebraic expression, right? Which is a series of values, constants and literals and operators that get evaluated. And this evaluation occurs and the result jumps across the equal sign to get assigned into that variable. Don't need that yet, so I'm going to get rid of it. So we only see one data type here. That's a data type. However, we have other data types going on in the background. This is what's known as a string. We just did not create a string to hold that. We could have said this, string prompt equals, you know, what is your height? Don't make this change, I'm probably going to undo it. And then cout arrow, arrow, prompt, right? That would work. Now we've actually stored it in a variable rather than using it as a literal right here, but you know, it's still a literal there. But this could be read from a file, read from a configuration file. So if you needed to translate this into French, right, you might not have to modify the source code. You might just have to modify a configuration file in order to do all the translations to French.
Does this work the same as Python, where you can grab, let's just say, a number from a separate file?
Yeah, we could open a file and read from the file, and we could read all that data out, and we could turn around, you know, read it in, and then perform some calculations and save it back out. Exactly. And the syntax is kind of cool, because once you create a file, if you want to write to a file, if you've created your file handle, it's called fout, then writing to the file is as easy as doing that. And reading in from the file, if you call your file handle fin, is as easy as doing that, which is even a little bit cooler than Python, to where your read statement was a different syntax from your input statement. But in this language, it's the exact same syntax, whether the output is going to the screen or a file, and whether the input is coming from a file or from the keyboard. All right. I'm going to go a little bit more, and then we're going to take a break. Algorithm is a set of well-defined steps. It's the recipe. Here's their algorithm. How many hours did you work? Wait for the user to enter the number of hours worked. Stored in memory. Display a message asking how much do you get paid per hour. Wait for the user to enter an hourly rate. Now this is even more detailed than ours was. I'm never going to give you an algorithm that's this detailed. I'm just going to say, you know, write a program that will ask the user for a temperature in Fahrenheit and convert it and display the results, right? That kind of thing. Wait for the user to enter an hourly pay rate. Once they do, store that into memory, multiply the number of hours by the amount paid per hour, store the result in memory, and then display a message on the screen that tells the amount of money earned, which must include the result of the calculation performed in step 5. Well, that is an algorithm. It doesn't tell us variable names, but an algorithm doesn't have to tell you variable names. So, machine language. Although the previous algorithm defines the steps for calculating the gross pay, it's not ready to be executed on the computer. The computer only executes machine language instructions. Now, I showed you, you know, Chip in the Box when he was reading his instructions and he was running those opcodes. I was trying to make that look like machine language. And machine language looks kind of like this. Well, that background sure is distracting. Let's copy and paste this. That's lame. All right. Here's a hello world program written in assembly, which is the closest thing to machine language that we get without just typing in pure numbers. We look at it. This gets saved into a file, and it's got some keywords that set some stuff up. And instead of load, it's using the word move. And it's storing into this register some length. And it's storing into this register some message. And it's storing into this register that, okay, well, where's message defined? We could scroll up and down, and here's our message, right? And here's, you know, something else. It's step by step, right? Move, 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 move. Just like what Chip in the Box is doing when I kept saying write or read. And then int 80. Well, what in the heck is that? That's not an integer. It's called an interrupt. An interrupt is when we're telling the chip to pause the system so it can accomplish some task and come back. An interrupt 80 just happens to be displayed a screen. This is incredibly primitive programming like you might do in 1980. We don't do things like this anymore, but when we compile something, it eventually gets turned in to machine code. This is a one-to-one correspondence with the actual machine language, which is just pure numbers. And then move this to here, and then move this to here, and then call another interrupt. I lied. Interrupt 80 doesn't mean a specific print. you set up the interrupt by storing something in one register and then another. And so a 1 and a 4 means display it to screen, and a 0 and a 1 means quit the program. All right, we're not going to talk about this much, but if we had this file and we saved it to a text file, we could run a program called an assembler, which would create an OBJ file, which was all the object code, the machine language instructions, and then we could run a linker, which turns that OBJ file into an executable. And then finally we have something we could actually run. This is machine language. Weird. Or this is assembler, which gets turned, assembly, which gets turned into machine language. We don't want to write that. Can you imagine writing, Fallout or, some extraordinarily complicated program by doing that? Once upon a time, that's what people did. But the invention of programming languages was a godsend. The people should have gotten Nobel Prizes for doing that. All right, let's stop and take like a 4-minute break, gang. All right, so an announcement, if you need one. Here's an online C++ compiler. There are a great many on the internet. This is just one that I've used. I want you to install Visual Studio, or whatever. No reason for the Mac users to do that. But if you get stuck and need to do some homework and you don't have Visual Studio installed, you still can do this, right? So I couldn't install Visual Studio isn't really an adequate excuse for not doing homework at all, right? Or my laptop crashed. Well, you can borrow another computer and then go to this website, right? Something like that. So I'm going to follow this link, and it's going to take me to a website where I can enter a program. Now, am I really going to enter a program? Probably not, but I'm going to copy and paste what I have from my Visual Studio. So I'm just going to select all. Control A, Command A for the Mac users. Control C for copy. Or right click and choose copy, right? You know how to do all this stuff. Go back to my page. Delete everything that's there just by backspacing over it. And then Control V as in vehicle for paste. And now I have a program that I could run. And it worked. What is your height? Yeah, let's see. I'm only 5 feet tall anymore. So I am 60 inches tall. What is your weight? I'm skinnier than I used to be, 100 pounds. All right. And there's my BMI calculated as 19. Notice it said pause not found. But that's just like I said. That system pause is for Windows only. And this online compiler is not pretending it's running on Windows. So that didn't work. So I could comment that out. Or I could leave it and just accept, that I'm going to get an error message at the end. There we go. What does this save option do? I don't know, but I'm going to click it. All right. Here's what I want you to do if you're having to do your stuff online. I want you to copy and paste your results into a Word file or a Notepad file or something so that you can submit it to me. So like Notepad, just paste that. Or create a Word document and paste it. Then you're going to take a screenshot as well. So I'm going to go back to my online compiler. I've run the program already, and I'm going to take a screenshot. So I'm going to click print screen, just like I did last time. Go to Word and click paste. And now I'm done. I have a file that I can save and upload into the homework Dropbox. Right? Do you have to do all that if you're actually using Visual Studio? No, honestly, I'd rather have the CPP file, right? But this is a quick and dirty way of getting it done. If you don't have Word installed on your computer, you can use a substitute called WordPad, W-O-R-D-P-A-D. And then you can still paste, right? And I could have pasted my source code into it as well. So you have the tools at hand, most likely on any computer that you sit down at, to do some C programming even without installing a compiler. So why do I want you to use a compiler? Because then your work is sitting there waiting to be reopened and stuff like that, and you can create complex projects with multiple CPP files and header files, and you're getting used to the development environment that professional Windows developers will be using. And other professional developers will be using other integrated packages like Xcode or Eclipse or something like that, you know, for Linux or Mac or whatever. I want you to have the full experience rather than just going to a website and typing some code in. But if you get stuck, you have a choice. You can do it that way. Un momento. Okay. So what I ought to do is I ought to then take 10 minutes and tell everybody to create a new program using the online editor, right? And just make it display to work, you know, something on the screen. I'm going to trust that y'all can replicate the experience that we just did. So machine language instructions are really binary instructions, such as whatever that is. And a machine language instruction will be composed of a number that represents the opcode, and then a whole bunch of other numbers that indicate the memory address and the register that it's supposed to be writing to and stuff like that. But rather than writing programs in machine language, 99.99999% of the people on the planet use programming languages. There are two types of languages. There are low level, communication with hardware directly. They're written in machine binary code. Or written, I wouldn't say often written. It's usually written in assembler, just like I showed you. That hello world application written in assembler. But a higher level language is something closer to human language. There's lots of high level languages. And the syntax for them is all different, although for some of them, the C family, they're similar. So C, C#, Java, JavaScript, C++, all of those have a somewhat similar syntax. So by learning C++, you're well on your way towards knowing these others. And if you learn Python, that's also great. And then there's some languages that people don't use too often anymore, but they're still actually used. People get paid to write Fortran and COBOL and stuff like that. Visual Basic is a cool language, and it's one of the ones we teach here. It's an online course. So here's what we do. From a high-level program to an executable file, we create a file containing the program with a text editor. Now, we use the text editor that's built into Xcode or into Visual Studio, right? But this is just pure text, right? I can go out to the directory and open it with Notepad, and I would see that text. There's my CPP file. If I right-click on it and choose Edit with Notepad++ or TextPad or anything, we will see that it's just a simple text document written in what is known as ASCII, saved in the ASCII format. If you haven't heard of ASCII, that's okay. We'll learn what it is after a little bit. So we have our text file. We didn't create it with Notepad, but we could have. Then we run the preprocessor to convert source file directives to source code statements. Well, what does that mean? The first thing that happens when we hit the green arrow is it runs the preprocessor. And I'm pretty sure that I mentioned that here. The programmer writes source code. The compiler turns it into exe. So the act of compiling is to run the preprocessor. It makes it obey all the # includes and this is and that's. So the preprocessor goes and opens that file and conceptually inserts it into this file. And it opens this file and conceptually inserts it. And it opens this file and it conceptually inserts it. Kind of like the import command in Python. But it's just literally doing a copy of the contents of that file and kind of pasting it in here. Now, it doesn't permanently change this file, right? After I run it, I don't suddenly see a whole bunch of new stuff up at the top of it. But conceptually, that stuff is now in the program. And the preprocessor does that. And the preprocessor can do a whole bunch more than just # include. I'll give y'all an example of that in a minute. I keep opening this when I really want my PowerPoint. Here we go. And then the compiler turns the source code into machine instructions, which is also known as OBJ, object code. And then the linker turns those object files into an executable file. Now, thankfully, we don't have to do all three of these steps. All three of these steps are done by just clicking the green arrow. But that's the first thing that happens, and then the compiler happens, and if the compiler fails because of syntax error, the linkers never run. So steps B through D are usually performed by a single command or button click anymore. And errors detected at any step will prevent the execution of the following steps. So if the preprocessor finds some error, like it's accessing a file that doesn't exist, it's not supposed to do the next thing. And then if the compiler finds a syntax error, then it's not going to link it. And we're not home free yet. Even if it compiles, when the linker runs, if something is missing, there's an OBJ file that's missing or something like that, then it won't link. Once all of these things are fixed, then we have an executable file, an application, an app file, an exe file, something like that. All right, so what is a preprocessor? We're just going to mess with this just a little bit. You saw me change, I think, the 703 into a constant. But I could have done this. # define BMI _ conversion 703. And then down here, I could have used that there. So, what the preprocessor does is just includes those 3 library files, and it also runs through here, and wherever it finds BMI conversion, it replaces it with the number 703. That's kind of neat. We can do stupid things with the preprocessor as well. What if we hate the word cout? Don't do this, gang. But you can do it just for grins, but I'm going to undo it, most likely. # define the word output to the word cout. And # define the word input to the word cin. All right, and now everywhere I had cout, I could use the word output. And everywhere I use the word input, I mean cin, I could use the word input. Right. So it's almost like I'm writing my own language. Right. Now what if I hate less than? Or what if I hate these asterisk symbol? I could define, # define the word multiply to the asterisk. And so my equation down here could look like this. Is there any reason to do that? Absolutely not. But you can. If you ever find a need to, if you want to shorten something somehow, you could write an entire equation as a form of a macro like that. I wouldn't. I would write it as a function, just like you do in any other language. But you could write it as part of the preprocessor. And the code should still work. And if you give this to a coworker to maintain afterwards and they see you've done this, they're going to come over here and hit you with a foam mallet because it's absurd, right? Especially that one, multiply. But you could. So the preprocessor does all that. The preprocessor replaces all these purple words with the equivalents up here. Now I'm going to undo that. We may find times when we want to do a little bit of that, though, within reason. Defining constants like that is not unreasonable. So those are the steps. Preprocessor, compile, link, and then run. Python didn't have a preprocessor. Python doesn't make OBJ files which are then linked. It's an interpreter instead, which works like a compiler, but it doesn't make an executable which is then run. It instead runs it on the fly right then and there. One of the interesting things about compiled languages like this is that they produce code that is specific for an architecture. Visual Studio, as configured on these machines, produces Windows code, right, for an Intel or an Intel compatible processor. You're not going to be able to copy this executable and mail it to your Android phone and then be able to run this BMI program on it. Within reason, there's an exception which I'll mention in a minute. You can't send this executable to your Mac friend and have them run it. Or our Mac users who make an executable can't email us that Mac application and us run it on Windows. It makes a platform-specific file. Now, the only exception is what if you have what's known as an emulator. Right, you probably have the idea of game emulators. You want to play, your Super Nintendo games on your PC. You can download a Super Nintendo emulator or a Genesis emulator or that kind of thing. Well, you can install Mac emulation software on your PC, or you can install PC emulation software on your Mac. But that's going through a lot of hoops in order to get something to run. Instead, what you would want to do is to take that C++ code and recompile it for that other platform. I'd rather give my C++ code to a Mac user and let them make it executable. Now, unfortunately, it's usually not as simple as that because, yeah, just printing a number in this console is one thing, but what about displaying windows with drop-down menus and, sliders and stuff like that? Those require libraries, and those libraries are different on each major operating system. The libraries that Linux uses are different than the ones that Mac uses, that are different than the ones that Windows uses. So the idea of using C++ to write an application that'll run on all three of those platforms is not real likely. So C++ is not something that you would make as your very first choice for a cross-platform application. Things like Python and Java, on the other hand, are written as interpreters rather than compilers. And what is an interpreter? An interpreter takes that text file and converts it into machine language on the fly and runs it right then and there on something called the runtime engine, which is like that emulation software for the Super Nintendo or the Genesis. It's emulating a computer. And you write that emulator, you write the Python emulator or the Java emulator for each platform, and then that same code on the same libraries will work on your Mac and your PC and your Linux. And so Python is not platform specific. It'll run on a whole bunch of different platforms. You don't have to recompile the code and give somebody a new app or a new exe. You just give them the new Python code and it runs. Same for Java. You can give them the Java file or the Java jar files, and they ought to be able to run it as long as they have a Java emulator, a Java runtime engine installed on their machine. So an integrated development environment, IDE. All the tools needed to write, compile, and debug a program. Here's our IDE. Mac users are using Xcode probably as their IDE. And there are a lot of different IDEs. It's just that this is the one that most Windows programmers use. It's the industry standard, so we're learning it. It provides us with a code editor, with a debugger. Well, what's a debugger? What if I do this? What if I put a click there? That's called setting a breakpoint. And then when I run, it says local Windows debugger. It wants me to enter a height. It wants me to enter. Okay, well, it stopped. The breakpoint told it stop running when it hits that line number. And I can move my mouse over and find out, oh, the user typed in 10 for the height. Cool. And then I can say, okay, but I want it to go ahead and run that line. And so there's a button I can press over here that'll cause it to run that line. But it's waiting for me to type something, right? So I'm going to say that I weigh 2 pounds. All right, now it's done with that line. It goes to the next line. This is called the interactive debugger. It runs it line by line. It hasn't run this line of code yet, so BMI doesn't have a value. It's got some kind of garbage value. It hasn't been initialized yet, right? We didn't say BMI is equal to 0 here. If we had, then when we hovered our mouse over BMI here, it would say that it was 0. But it doesn't. But we're going to execute this line by clicking that button. And now it has performed this calculation and stored the results in BMI. So if I hover my cursor over BMI now, it tells me that BMI is equal to 14.06. This is the interactive debugger. We can go through it line by line. And really, I ought to sit down and make us do, like hours of interactive debugging, because in the professional world, you're going to be using the debugger a lot. But I'll try to get y'all, at least some experience with it. And then when I'm tired of stepping it through line by line, I can just click the continue button and it'll run, until the next breakpoint. But there's no more breakpoints, so it would just finish the program. So that's the power of the IDE, is it gives us the ability to enter a source, to manage projects, to put a whole bunch of files together, to compile and link them and run them with a single click, to have an interactive debugger. That's why we like IDEs. Didn't always have them. In the 70s and the 80s, if you were going to write C code, you used a text editor, and then you ran one program to compile it, and you ran another program to link it, and then you ran it by hand. So things are easier nowadays. But then we write far more complicated programs than anybody did in the 70s and the 80s. What is a program made of? Sugar and spice and everything nice. It's also made of keywords. Program defined identifiers. Well, we've seen keywords like if statements. We didn't have any if statements in our code, but we could have. An int, right, or float. We had some floats. Things like that. Programmer defined identifiers are the function named and the variable names. We only had one function called main, but we had several variables. We had 3 variables. Operators, those are the symbols. There's more operators than we might expect, because this counts as an operator and these count as an operator. So all in all, I see quite a few little operators. I see that one, that's 1, 2. I see multiplication, that's 3. I see division, that's 4. So this program, by my reckoning, has 4 different operators. Oh, and the equal sign, the assignment operator, 5. So these are identifiers and these are operators. 2.5 hours is a long time for a class, but we're tough. We can handle it. And then it's got punctuation and syntax. Well, what's the punctuation? It's just the semicolons, And then the syntax are the rules in which, things have to be in front of other things. You have to have a space between the data type and the variable name, and stuff like that. So keywords are known as reserved words because we cannot make a variable named if. Right? I cannot go here and say, I'm going to make a variable called if, and it's going to be a double if. Nah, can't do that. All the blue words are keywords, so I could not create a variable called namespace. Why would I want to? I don't know, but they're reserved. They're part of the language. They're the verbs that make up the language. They can't be used for any other purpose. So we've seen namespace, we've seen int, we've seen double, and we've seen return, even though I left return off. Honestly, we should have a return statement at the end of our program, and I can't believe I left it off. I'm going to need to remember to modify my boilerplate. We should have a return 0 at the end of our program. Well, what does that do? I didn't do that in Python. You're right, you didn't, because Python is running in its own little sandbox, its own little emulator. But a C executable is called by the operating system, and when it's done, it returns a value back to the operating system so the operating system can decide whether it was successful or not. And you can return a non-zero error code, which could then be checked by the program that ran the executable, like a script file, a batch file. So since this program is written and declared that main should return an integer, we're going to abide by that. We're going to return an integer. So from now on, I'm going to add that to my boilerplate, and there's going to be a return 0 at the end of all my programs, just for completeness, just for correctness. Programmer defined identifiers. The programmer makes these names up. The names are just for our convenience. I'll say things like variable names aren't important. That's not exactly what I mean. But what I mean is that didn't have to be called HT. If I do a rename and I call it Tony Stark is awesome, that worked, right? The program will still run. It's stupid, right? Why would I want that variable name? But the variable name is meaningless to the computer. It doesn't care if I call it Tony Stark is awesome, or if I call it X123, or some curse word in Polish. It doesn't matter to the computer what that variable name is. It only matters to us. But we're supposed to be choosing good variable names that we understand what they are. So I could have called it something other than HT. I could right-click on it and rename it and say height in inches, like that, right? Now that's not as silly, right? What is your height? Store to height in inches. I could do the same thing for WT. I could rename that and make it weight in pounds. And then the program's a little bit more self-documenting in a way. When we're looking at it, we can see the variable names. We look at this formula. We understand exactly what these pieces of data mean. Now, when I'm having y'all follow along with me, and if I asked you to type in weight in pounds, 50% of us, probably including me, would make typos. So I go with shorter variable names for our examples. But you can always go back and make your variable names better just by renaming them. Highlight them, right-click, rename, and give yourself a better variable name. Each variable name is known as an identifier, and there are rules for how you can name the variables. If you've done Python, you're probably familiar with the idea that there are variable name rules. Rules like identifiers can be letters, digits, and only one specific symbol, and underscores. On Windows, you can also use $signs, but I don't think that that's true for all compilers. If you really wanted to, you could create a variable that had a $sign, int $sign is equal to 3, but that's going to look nuts. Nobody would want to see a $sign there, and it wouldn't work on every compiler. So we're just going to stick with the fact that identifiers can be mixtures of letters, digits, and underscores. One rule, though, cannot start with a digit. Those are our two rules for function names and variable names. No spaces, so we can't do my space age is equal to 30. That's an error because it's got a space in it. If you wanted to, you could put an underscore there. It kind of serves as a space. Now I'm still getting errors because it's outside of any function, right? But that would be a valid variable name. Some people like underscores. Some people like to do what's known as camel case. Why camel case? Because it's lowercase and then suddenly there's a hump in the middle, and then there's more lowercase, right? And you can have extra humps, right? My age in months, right? There we go. There's 3 humps in the middle of it. It's a 3-hump camel, whatever that is. So identifiers are variable names and function names, and class names and structure names. But for now, we're just going to go with function names and variable names. The user picks them. The programmer picks them. They mean nothing to the computer. You just have to use the same variable name every time you mean it. But they mean a great deal to us, or they can. But they mean a lot to us because they help us understand what the program is. So we want to choose good variable names. What is a good variable name? Not single letter variable names. Yeah, for this short of a program, I probably could have gotten away with using H for height and W for weight and B for BMI. But that's kind of lame. And if you have thousands of lines of code and you see all sorts of single letter variable names, you're not going to be able to figure out what the program is doing. You want good variable names, which are like actually words, right? You know, multiple characters long to explain what it's doing. However, when I'm giving code examples up here, I'm going to use single letter variable names, right? If I'm writing a loop, I'm just going to use X as my counter, right? Or I as my counter, rather than, you know, use the whole word counter, which takes longer to type out. And that's okay. For counters and, you know, index values and stuff like that, going ahead and using X and I is industry accepted. But you don't want to use single letter variable names all through your code. You want to pick good variable names, meaningful variable names. And then there are the operators. Addition, subtraction, multiplication, division, the assignment operator, the equal sign. There are comparison operators like less than and greater than, and less than greater than, or less than equal to, greater than equal to, and equal equal. And then this is called the stream insertion operators because they read from the stream or they write to the stream. That's a funny term. We weren't using it before. But CIN is an input stream from the keyboard to the program, and cout is an output stream from the program to the screen. And then there's punctuation. Commas are punctuation, semicolons are punctuation. You need something to separate the, you know, the lines of code, and you need something that separates the parameters in a function call. Like when I had that POW call, if I still had it in there, you know, like x is equal to POW a comma 2 in parentheses semicolon, right? You needed something to separate those two things, so you used a comma. That's part of the punctuation. You needed something to mark the end of the sentence, so you use a semicolon. And I think I said this before, but you don't put semicolons after preprocessor statements because it's not a C statement. It's a preprocessor statement, and the syntax of the preprocessor statement is that you don't use semicolons. You might be able to get away with it sometimes. If I put a semicolon there, it might not break it, but you don't want to. So the syntax are the rules of the grammar. Just like in Spanish, the adjective follows the noun, but in English, the adjective precedes the noun. Like we say, the red mountain. In Spanish, it is whatever the word for mountain is, followed by the word for red, roja or rojo, right? So instead of saying the green tractor, we say the tractor green, right? And that's true for a lot of the languages, you know, Italian and French and stuff like that. The adjectives and the adverbs follow the things that they're modifying. That's just the grammar. And if humans are smart enough that if I walked up to you and I said, please hand me the pencil yellow, you'll look at me and cross your eyes, but it's understandable. But computers, the syntax needs to be precise. It needs to follow the rules precisely. And the syntax dictates the order that operators can be used, which symbols can be used, what operators there are, and where the punctuation goes. And what is a variable? I'm going to give you a very specific definition for a variable. It's longer than this. I want you to memorize this, and I wish we hadn't had a student just walk out because she's not going to memorize this. All right, so a variable has 4 components. It's got a name, it's got a type, it's got a value, and it's got a memory address. Normally, we don't care about the memory address. I don't care that age is being stored in memory address 2,335,004, right? I can find that out in this language. In a lot of languages like Python and Java, there's no way you can even find out where that data is being stored. But C++ goes ahead and lets you figure that out, which makes it powerful in some ways and more prone to crashing in others if you're not careful. That's done by something called pointers. But normally we don't care about the memory address. We care a great deal about the name, because without the name we don't know how to use it. The compiler needs to know the type so it knows what kind of data is stored in it, right? We would not be able to store a number that the user typed in if it was declared as being a string, because a string is a series of typewriter characters, and you can't do math on a string. You have to convert it to a number. And then it's got a value. It has to have a value, or else there's no point in having that variable, right? So when the user types in that their height is 60 inches, that's its value. So say we have something like this: int age equals 32. The name of the variable is what? Yeah, and what is the type of the variable? Int. And its value is 32, and its memory is a mystery. Or we could have, string name equals Fred. Same business. The name of the variable is name in this case. Tell you what, I'm going to make this say first name. The name of the variable is first name. The type of the variable is string. The value, the data that's stored in it, is Fred. And who cares about the memory address? Sorry, probably close that before people were done typing. Now in Python you had a limited number of data types unless you used a library to give yourself more. You had ints, and you had floats, and you had booleans for true false values, and you had strings. That was pretty much it. C++ gives you umpteen billion different data types, so that you can specify whether you want that integer to be 2 bytes wide or 4 bytes wide or 8 bytes wide, whether you want it to be able to be positive and negative or just positive. Kind of crazy how many different data types there are. But we're just going to pick a few and we're going to run with them. So we're going to have a data type that we use for integers. We're going to have a data type that we use for floating point. And we're going to have a data type that we use for string. Now, why does it have so many? It's because this language was invented originally as a C programming language to control hardware for, for phone company switches, to control the switching computers. And so it was very byte oriented. I want to change this byte, I want to change that byte, I want to change the other. And so it was designed to be very picky and very specific about the size of the data that was being manipulated. Python's not written to do that, right? So, and Java isn't either, so it doesn't need that many different data types. We will see a list of integer data types, we will understand what they mean, and then we'll go back to just using ints most of the time. So to create a variable, we have to give it a type. This is called a variable definition. Ours is of type double. Oh, and also, by the way, so is rate and pay. While you're defining your variable, while you're creating it, while you're declaring it, you can also initialize it. You could say that the hours is equal to 40, and the rate is equal to, we're earning $12.50 an hour. And the pay is equal, well, we haven't calculated it yet, so it's 0. That's totally legit to do it like that. But as I told you, a lot of programmers prefer to list the variables, vertically, one per line, rather than to stick a whole bunch like that. But it's not illegal to declare a whole bunch of variables on one line. But they do have to all be of the same type, right? Somehow I lost where I was. Right. I can't do hours, comma, rate, comma, pay, comma, name. Right. Because name, one of these things is not like the other. Yeah, so said Sesame Street. This is true here, right? Name is not going to be a number. It's going to be a series of characters inside quotes. So you'd have to put that on its own line. It'd have to be a separate declaration, string name. Like that. Many different types of data, as I mentioned. So a variable holds a specific type of data. Python is happy to erase whatever kind of data type you have and replace it with a new one. If you say name is equal to Fred, and then you turn around and say name is equal to 123, and then you turn around and say name is equal to false, it rearranges that variable. It reconfigures it on the fly. Not true of this language. Once you say that name is a string, you cannot store an integer in it or a float. You might be able to find some representation, some string representation that could be converted, but it's not a compatible data type. A string is not a float. A string is not an int. So if you create an int, you can't store a string in it, and vice versa. Once you declare the variable, it is of that type. Input, processing, and output. Generally, programs do these three steps. They gather some input, they process the data, they display the results as output. And in the real world, they don't just do those three things. They usually loop to keep repeating this process. Right? Playing Pac-Man. It's gathering input in the form of the direction that your joystick is pointing. And then it processes the input data. It decides that if you have the joystick pressed up, that it's got to update Pac-Man's position by a pixel going north. It's got to move in its memory all of the positions of the ghosts. It's got to keep track of all the dots. So all that processing does after it gets the input, and then it displays the results. It takes whatever's in memory and it draws a new screen based on the new position of Pac-Man and the dots and the ghosts and stuff. Then it loops, right? Because if you ran it and it just moved the Pac-Man up one pixel and then exited, wouldn't be a game, right? And so it keeps looping, gathering more input, gathering more input, gathering more input. Input, process, display. Input, process, display. Input, process, display. Computers are what loops are all about, essentially. The programming process. I think we're going to call our day done as soon as we get to the end of chapter 1, which would mean that we get out early. I don't know if that's such a great idea, but I'm losing my voice. Y'all are probably tired of listening to me. Maybe we'll grant ourselves that luxury. The programming process. Clearly define what the program is going to do. I love this next line. Visualize the program running on the computer. That reminds me like of yoga or meditation or something. Visualize the program running on the computer. Anyways, you just have to figure out what the program's supposed to do. Right? I'll give you instructions that defines what the program's supposed to do, but it may not be specific enough. If I just say write a program that converts Celsius to Fahrenheit, that's not a lot of information. You're going to have to figure out what it needs to do. Well, maybe we ought to ask the user for the Celsius, and then do the calculation, and then maybe we ought to display the result. And maybe we're going to let the loop over and over and over so that the user can convert a lot of temperature. You know, that kind of thing. You make those decisions if I'm not specific. I could be very specific, right? I could give you like, you know, a 2-page specification of how I want your Celsius program to work, but I like to give you all a little bit of freedom usually. I will list a couple of bullet points and then have you go and do that. And then you use design tools such as hierarchy chart, flowchart, pseudocode. Well, we're not taking fundamentals of programming, so I'm not going to do flowcharts. I'm not going to do pseudocode. I'm not going to do hierarchy charts. I'm past that point. We check the model for logical errors. Sounds great. This isn't a software engineering course, so it's a programming language course. And what do I mean by software engineering? Software engineering is a discipline of how you define your specifications and how you create something that's testable and you create a test plan, stuff like that. And those are skills you actually need to learn. And I want us to teach a class in software engineering, but we don't have one yet. Type the code, save it, compile it. That's generally, you know, if you tell somebody to write a program, if they've been programming long, they usually immediately jump into step 5. But you could not write a great big game just by, you know, whizzing it off at the top of your head. You know, I've been programming long enough that these examples, take this kind of input and convert it, using this formula and display the output. Yeah, I could write that off the top of my head. But if it was anything more complicated than that, I would need to do some things. I would need to get some specs. I would need to do some definitions and stuff. Correct any errors found during the compilation. You run it and you find out that you've misspelled the word circle. You've left off a semicolon. You keep doing that. Wash, rinse, repeat. How do you kill a programmer? You make them wash, rinse, and repeat until they start. I don't know. So eventually, you fix all the syntax errors. You're ready to run the program. You run the program. You test it. Now, when you're testing it, you don't just run it once. Or yeah, you do, but that's not good testing. What you're supposed to do is to test to make sure your program works. You prove it works, and then you test to see if you can make it break. Now, we're not learning the techniques at the beginning to make code unbreakable. So, in general, we're just going to test it to make sure it works, right? I typed in a BMI of, this and that. But what if I had messed up? What if I ran it and I said that my height was, 0 and my weight was 120? BMI calculated as inch. All right. Well, I've broken the program. It didn't crash, but it didn't display good output, and it didn't warn me that it was displaying bad output. All right, let's see if we can break it even further. What is your height? 72 inches. All right. I broke it because I gave it bad input. I typed in the word inches, and that's not the expected input. It didn't even wait to let me type in a weight, and then it calculated my BMI as 0. So the program is easy to make it malfunction. In the real world, you would not want to make your program this vulnerable, right? To where it could crash this easily, to where it could display output that easily. So you test your program to make sure it works, and then you try to test your program to see if you can make it fail. And if you can make it fail and you know how to stop it from making it fail, you make those changes as well. And in a programming team, sometimes there are people who are dedicated to testing the program. Right? You've heard of video game testers, right? They play the game and find out if it breaks. But for any kind of large programming project, you have people who are testing the thing before it gets sent to the users. You have a test department, and the test department and the programmers sometimes start hating each other. No, I'm kidding. It's all a happy family. Everybody works together. So you correct the errors that you find when running the program. You repeat steps 5 through 8 as often as necessary. Well, really, sometimes you go back and jump back even further, right? Sometimes you need to modify your model, right? We realize that we did not take overtime into account. So we have to go back and adjust our programming plan, in order to accommodate the fact that some people get overtime. We would have to change our model, our algorithms, and then we could type some new code. So, sometimes you have to jump way back, all the way back to step 1 to revise. And you'll find, if you become a professional programmer, that anytime you write a program, the users are going to want it changed. Absolutely every time. You write something, they want changes. And quite often, those are legit, and quite often they're asking for changes that they should have told you to begin with, and you can become frustrated with that. And when I say frustrated, it can be disastrous if you got some bad specifications and you go to the specs, and those specs, and then there are a lot of fingers you're pointing because it didn't work. It's just a fact of life that if you're given bad specifications, you're going to write a bad program. Not your fault, but maybe you could have recognized that the specs were bad, but sometimes you're not psychic. You don't know what format the data is supposed to be stored in if somebody gives you the wrong specs. The difference between procedural and object-oriented programming. Procedural programming. We've just written a procedural program here. Right? Starts at the top, asks for some information, does a calculation, displays it. Object-oriented programming would look more like this. I'm not going to write an object-oriented program, but it could look something like this, right? Patient equals new patient. Something like that. So patient P1 is equal to new patient. P1 dot input weight. P1 dot input height. P1 dot calculate BMI. And then P1 dot save to file. Something like that, right? And then P1 dot display to screen. That looks considerably different than what we wrote. Well, for one thing, we didn't save their file, right? But maybe you see the difference because you could create several different patients and keep track of them all, right? You can make a second patient and get their weight and their height, then a third patient and a fourth patient, and you could make, 100,000 different patients and add them to a list, or display them on screen or something, whereas this thing is only able to hold 2-3 pieces of data at a time. If it was written as objects, then each object can contain copies of those 2 or 3 pieces of information. So object-oriented programming is the only way that programs were ever allowed to become as powerful as these Windows-based programs, right? Because every menu is an object, every scroll bar is an object, every button you can click is an object. The data that is saved to the file is defined as objects. The printer that you're printing to is defined as an object. It's a model. An object is just a model that's got data and it's got some functions. So Pac-Man could be implemented as an object-oriented game. I'm absolutely sure it wasn't, because but it could be, right? Because what Pac-Man has is he's got an X location and a Y location. I hope you all know what Pac-Man is. Got an X location and a Y location, and he's got a direction that he's going, and he's got a number of lives. He's got the speed at which he's traveling, if you're playing one of those versions of Pac-Man where he can speed up and slow down, right? And then there are other information, right? Like there's the maze information. How many dots are left on the screen, right? If you eat one of those power pellets, how long did it go turn blue? That kind of stuff. All that could be stored in a different object. And then you could make a game where you had multiple Pac-Mans on the screen at the same time. I've seen a game like that down at the theater. It's kind of fun. Pac-Man Royale or something, I don't know. If 4 players playing Pac-Man at the same time trying to eat each other, I guess. So object-oriented programming is a kind of a different paradigm. When you did Python, you did almost all pure procedural programming. Now that we're starting C++, again, we're going to do procedural programming for the most part, but we will progress to being object-oriented programming towards, the last third of the class or so. And then if you go and take Java from day one, you're doing object-oriented programming just because that's how the language is organized. Absolutely everything in it is an object. Ta-da, we are done with chapter 1. How about that? So in a procedural program, the focus is on the process. Ask the user for the height. Ask the user for the weight. Do some magic. Display the results. It's a process. Blip, 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 blip. Object-oriented programming, the focus is on the objects, which contains data and the way you manipulate that data. Right. I'm going to read in a file. I'm going to read in an image. Now I want to apply a filter to that image. Now I want to resize that image. Now I want to display that image on the screen. The image is an object, and it would have these functions which manipulate the object. And when you're talking about objects, functions are not called functions, they're called methods. Methods are just functions that are part of an object. And then so-called messages sent to the objects, perform operations. Well, that's one style of object-oriented programming. None of the languages we have here use messages sent to objects. Instead, you call methods. I think we're done. Do we have any questions? We are going to need a homework assignment for those who get Visual Studio installed. Now, we've written a BMI program. We're going to write something else. We're going to write, one of those dreadfully exciting conversion programs. Some kind of program that will convert like from pounds to kilograms. So here's what our homework is going to be. Homework. write a program that asks the user for a weight in pounds, converts or stores the user's input into a variable called LBS, converts the pounds to kilograms using the following formula, storing the result in a variable called KGS, and the formula is KG is equal to, or KGS is equal to LBS divided by 2.2. And I'm going to go ahead and get the a more exact value because that's not quite right. 1 kilogram in pounds. Google, tell me the answer. Ooh, there it is. That's real precise. Let's use that value. Pounds divided by 2.20462. And then lastly, display the result. All variables should be of type float. That'll be your homework. And based on what we've done today, it might be really easy for you, right? It might be a 5-minute program. It might not be, that's okay. It's okay either way. If you get stuck, ask me for help. I could have just not told you the formula and told you to Google the formula. But if I ever do that, I will add to the instructions, text me if you get stuck, right? If you can't find the formula to calculate the surface area of a of an octahedron, well, it's not a math class. I may tell you to find the formula online, but if you can't get it to work, then go ahead and text me and ask me for the formula, and I'll give it to you, right? Just because what I want you to concentrate on is the programming, right? Not on your research. This isn't a research class. It's a programming class. But on the other hand, I don't like to spoon feed you everything. But if I don't spoon feed you and then you need a little bit more help, I'm happy to help. All right, guys. Are y'all willing to end a little bit early? Anybody object? I see some people glaring at me. You want to keep going? No, I'm kidding. I'm kidding. I'm kidding. All right. Let's make a Dropbox, or maybe there already is one, for our work. You don't have to submit a screenshot, but I do want the CPP file that you did today. Or at the very least, I want you to submit just a statement saying that you were here, but I'd rather have your notes. This one, unlike D2L, actually lets you enter a command, a line of text, by the way. But guys who are watching this at home, I would not accept this. I would not give you credit for what I'm about to show, which is that if we, I don't even know why I'm showing this to you, just I guess because I noticed it myself. If I go to assignments, if you ever need to send me a message without attaching a document, you can do it like this. You go here, submit assignment, and there should be a place where you can put a comment, right? You can click submit without having attached a file. Normally I'm going to want you to attach a file. However, you may have noticed that there's an assignment folder called Hey Prof, Give Me Points. If I make a mistake in your grading, I want you to go into that folder, click Submit Assignment, and say, can you please check homework 7? You said it was great, but you gave me a 0. Now, if I said it was great, I probably didn't mean to give you a 0, right? So you'll want to tell me about that. So that's what that folder is called. And you don't need to put a document just to tell me that I need to regrade homework 7. On the other hand, you know, sometimes you might want to attach something there. But that makes sense. Everybody know how to get their CPP file and put it in the Dropbox. Then have a great weekend. Please try to get Visual Studio going. Can't get Visual Studio going. The homework is going to be due, you know, midnight Tuesday, but it'd be cooler if you got it done over the weekend. Okay.
You tell me if I did put the right one on
Oh,
there.
I'm sure you did. I'm sure you did. Did I take roll? Don't run out.